Okay, hello everyone. Welcome to Stat 479, Lecture 13. We're in the middle of discussing regularization, in particular, one very important regularization algorithm related to the lasso or L1 regularization. So for today, I'm hoping to finish the discussion on the lasso, but the first thing I'm going to do is to just spend a short amount of time, maybe 10 or 15 minutes, just discussing convex functions, in particular characterizations and subgradients, because obviously convexity has been a topic that's come up a lot throughout this course, and I haven't really properly defined it or gone into any detail about it, and I thought that was reasonable when we were kind of looking at scenarios where everything was nice and smooth and twice differentiable and so on. But when we went into the lasso and started to talk about like subgradients, I think I need to go back into and discuss just convex functions a little bit, just so that to give you a bit of a geometric picture of what's going on. And this will be kind of useful to supplement what we've learned about the lasso and other things we've mentioned about convex algorithms. Then I'll kind of return back to the main material. So that's the lasso. In particular, we talked about the soft thresholding algorithm, which is sort of the basis for a lot of the lasso algorithms. So I'll finish discussing that and then go into the analysis. So really discussing kind of how does the lasso potentially improve the performance in terms of mean squared error. So I'll first spend about 10 to 15 minutes just talking about convex functions because they're such an important topic. So this is a bit of a detour, and here I'm really focusing on convex functions in one dimension. It's pretty easy to generalize these to multiple dimensions. And I won't really focus on that too much because if you know what's kind of going on in one dimension, it's reasonably straightforward to generalize. Just want to give some intuition as to what's going on in this case. So I haven't actually properly defined a convex function. So just to be clear, the underlying definition of a convex function is as follows. I'll kind of give some intuition for it, but it just says that f is a convex function if for all x and y in R and alpha in 0 to 1, you have this, like if you take any convex combination, alpha x plus 1 minus alpha y, that's less than or equal to alpha times f of x plus 1 minus alpha times f of y. So intuitively, all that really means is that the function curves up, or what the definition is saying exactly is that all line segments lie above the function. So just to give you some concrete examples to kind of keep in the back of your mind of convex functions, we've talked already about the quadratic f of x equals x squared. And that's been kind of seen a lot throughout the course. And that kind of has this nice kind of curving up shape. We've also mentioned e to the x. And then we've also, in the previous lecture when we talked about the lasso, we mentioned this absolute value of x function, which is also convex. And we'll kind of try to illustrate that through these definitions. So if we think about this first example of f of x equals x squared, if we draw a line segment, between any 2 points, which I'm doing right now, you can see that, that line lies above the curve. And you can do that for kind of any other 2 points. If you take any 2 points, the line segment lies above the curve. And that's essentially the definition of convexity. And you can see that, and we don't assume anything about differentiability here. This is just saying that, this is just saying that any line segment lies above the curve. And you can see similar things are true for e to the x here, that any line segment lies above the curve. And that's what the definition is saying. And similarly for the absolute value of x, if you pick 2 points and you join a line between them, it lies above the function. And I mean, obviously, if you pick 2 points that lie on, 2 points like this, they're going to lie on the function, but that's still less than or equal to the actual function. So these are 3 examples of convex functions because all their line segments lie above the function. So no notion of differentiability required in the underlying definition of convexity. And one of the reasons I didn't define it earlier was because we always kind of, until last lecture, we always had convex functions that were differentiable. So we kind of characterized the definition through differentiability. But obviously when we started to talk about the lasso, we didn't have differentiability anymore, which is why it's kind of important, I think, to go into like the underlying definition of convex functions here. Okay, so just to give a different just to kind of give different characterizations. And this will be useful when we talk about what we've already spoken about with twice differentiable, like the double derivative being bigger than zero, if it's differentiable or if it's twice differentiable, and it'll also lead to the notion of subgradients. So now we're going to start to assume differentiability and see how we characterize things. So an alternative characterization. So if f is differentiable, and this is only assuming once differentiable, so okay, so what I'm saying here is, so f prime of x is the derivative. And so in words, what this actually means is that what this means is that all tangent lines lie below the function or curve. So let's go back to kind of our examples here. So if you think about, again, this is related to this notion of curving up. So if we think about the tangent line here, this lies below the curve. So this is, so if this is your x0, you can see that the tangent line kind of lies below the function. So that's kind of, and you can also see that it's true if you pick an arbitrary point x0 here, the tangent lies below that. And again, this is because the function curves up. And so this is kind of another different characterization of convexity, and this is going to be really useful when we talk about subgradients. We can't really talk about this second notion for the absolute value of x, because this is obviously not differentiable at every point. But you can certainly see that if you pick any point, the tangent line, any point that's not zero, the tangent line kind of lies again on the curve, which still follows the definition. It has to just be either below or on the curve. Okay, so and why, like how come this is saying this? You can kind of clearly see that the tangent line at x0 is kind of a function of the form f prime of xi times x0 times x minus x0 plus f of x0. So that's the tangent line, and then and so this is and then we're saying that f of x is bigger than and similarly, if f is twice differentiable, then f is convex if and only if f prime prime of x is bigger than or equal to 0. So this is kind of this is related to this notion that the function curves up, because the double derivative kind of is referred to as curvature. So f prime prime of x is often called curvature. Because that's measuring how quickly the gradient's changing, or how, and so if that's positive, that's saying that it's kind of curving up. It's getting bigger. And so clearly, we know that we've done these calculations before, but if f of x equals x squared, then f double prime of x is equal to 2, which is clearly bigger than 0. If f of x equals e to the x, then we know that f double prime of x is e to the x, which is also bigger than 0. So again, like we have strict we have convexity for these two examples. Okay, so one thing to note here is that 1 and 2 do not apply to the absolute value of x, since it is not differentiable. At x equals 0. So this is why we introduced the notion in the previous lecture of the subgradient, which I didn't kind of strictly define, which I'm going to define here. So subgradient, and this is kind of related to definition related to the first characterization of convex functions. So okay, so what I'm saying here is a subgradient of a function at x0 is a number c such that f of x minus f of x0 is bigger than or equal to c times x minus x0. And then we can say that if f is differentiable at x0, then c is unique, and c equals f prime of x0. And so this is kind of like, this is note that we don't assume differentiability here, and this gives us a definition of a subgradient. So this is kind of the definition that we have here. So let's so one thing to note is that if f is convex, they're always so basically what it is, you want a line that I'm just kind of trying to describe in words what's going on, because it's kind of easier to think about both in terms of pictures and words. Sorry, I'm stuck here. So in words, in words, C is the gradient of a tangent line that goes through x0, goes through the point x0, f of x0, and lies below, and it lies below f of x. So let's kind of refer back to this example 3. F of x equals absolute value of x. So for x not equal to 0, we clearly have that f is differentiable. And therefore C is equal to, or we'll say x0, C is equal to f prime of x0, which is just, in this case, it's just going to be the sine of x0. So C is unique. Now, the interesting thing, and what we saw in the previous lecture, was that for x0 equals 0, clearly we're not differentiable. But can we draw a line that kind of goes through the point 0, 0, which is here, goes through the point 0, 0, but actually lies below that? And you clearly can, if you provided that the gradient's not too big. So, kind of this line lies below it, this line lies below it. So kind of as long as the absolute value of C is less than or equal to 1, f of x minus f of 0, which is 0, is greater than or equal to C times x minus 0. So, here clearly f of 0 is 0. So you can kind of just say that f of x is bigger than or equal to Cx, as long as the absolute value of C is less than or equal to 1. So therefore, subgradient, or it's sometimes called subdifferential, of f of x is absolute value of x it's plus 1 if x is bigger than 0, as we've spoken about. It's negative 1 if x is less than 0. And it can be anything between negative 1 and plus 1 for x equals 0. So see a note that subderivative or subgradient at x equals 0 is not unique, and that's certainly possible when you have convex functions that are not differentiable. Okay, so this is the notion of the subdifferential, which is very important in the previous lecture, and I Okay, so this whole topic of convex functions, convex optimization, and so on is a really, really rich area that's very useful in computer science. Really, in all areas, it's probably one of the more useful courses that or more useful concepts, because it just comes up in so many places, like it does in this course here. And so, if you want to read more, I'm not going to kind of delve too much further into it. I encourage you to read Convex Optimization. There's this book by Boyd and Vandenberg. I wouldn't suggest reading the whole book, but because it's about 700 pages. But if you wanted to focus on maybe the first few chapters, that goes into convex functions in a fair bit of detail, just to give you a bit of kind of bit more geometric intuition and other things. So if you have kind of more questions about it or want to read more, I highly recommend this book. Okay, so that's just our little detour to convex optimizations. So returning to the main topic is the lasso. So let's again go back to the statistical framework to remind everyone kind of what's the scenario we're looking at, what kind of algorithms that we're looking at, and then we're going to kind of build towards the analysis that we'll work on today. So remember, with our statistical framework, we always start with the data. So we have this data here, x1i, x2i up to xpi, yi, and then it's convenient to write this in matrix form. X is in R to the n by p, y is in R to the n. Okay, and if we talk about the model. So the linear model here we have is y equals so we have this linear model where y is xb plus epsilon. So b here is in R to the p. That's the parameter of interest. And epsilon in R to the n is the noise. And here we've conveniently assumed that it's multivariate normal. A lot of the ideas go beyond that, but as we'll see, the analysis will be a lot easier when we assume that. Okay. And the other key thing is that we assume further that B0, or the so this is referred to as kind of the sparsity assumption. I mean, in mathematically, it might look a little bit complicated, but all it's really saying is that only S variables have any influence on Y. So, we're kind of saying that even though we have P variables, only S or only up to S influence Y, but we don't know what they are. So, as I mentioned in the previous lecture, this is related to model selection. Choose the S variables out of P total, and that's kind of there's ways to do it, and we kind of focus on the lasso. So for the algorithm or estimator, we talked about the lasso. Okay, where this L1 norm here, this is where that absolute value expression comes in. It's the sum of these absolute values of Bj. And so note that, the L1 norm of B is convex, but not strictly convex. And the intuitive reason for that is because when we drew those tangents, they kind of lay on the curve rather than below the curve, which is which is why which is why it's kind of convex but not strictly convex. Whereas if you look at the quadratic or the exponential, all those tangents lie strictly below the curve. So that's why those are strictly convex, whereas the L1 norm is just convex but not strictly convex, and so therefore beta hat L is unique if or a sufficient condition for uniqueness is that the rank of x equals p, because that ensures the strict convexity of the first part. So rank of x equals p, since this implies y minus xb squared is strictly convex. And that's when you have unique minimizers when you have strict convexity usually, and a few other properties, but strict convexity is kind of the first key property that we need. Okay, and so today so we finished discussion on soft thresholding. Algorithm, and I'll briefly just touch on very, very briefly on some other algorithms, and I guess the main focus of today is analysis. How close is B hat L to B? And this is going to be in terms of obviously n, p, and sigma squared, which is always going to be in terms of, and then lambda is going to be important. So lambda, and then s, the sparsity parameter, and we're going to see all of those kind of show up in the mean squared error bounds. Okay, so the basis for many algorithms, I'm only going to touch on one kind of idea behind these algorithms, which I spoke about in the previous lecture, but I'll kind of touch on again today, which is this notion of soft thresholding, because it's the basis for a lot of other algorithms. And so again, I repeat the assumptions that we're making. So, or there's one key assumption we're making, which means that which is that X transpose X over N is the identity matrix. And as I mentioned previously, although this seems like a very strong assumption, in some cases you can kind of standardize your data to make sure that it holds. And in other cases, for example, like the matrices that you generate using random IAD entries, like you've done in the first two homeworks, or and you will also in the third homework, that, although it may not satisfy this assumption exactly, it actually satisfies this assumption approximately. Okay, so so this is the key assumption, and we made this also when we're talking about ridge regression. And then we're also going to use this notation that y tilde equals X transpose Y over square root of N. And why is this useful? Because y tilde is data dependent. So clearly this is a function purely of the data, and also that we can see that y tilde equals, if we plug in the model, and then if we plug in the model. And so we can kind of see that this is just okay, and this is going to equal to root n times b plus epsilon tilde, where epsilon tilde is multivariate mean zero and variance I sigma squared, sorry, I p by p. And the reason for that is because, you know, using what we already know, this is just sigma squared times x transpose x over n is the covariance. And, we know that x transpose x over n equals the identity. So this kind of gives you a way of thinking of y tilde as in some sense, like just the signal. So this is like kind of the signal and then plus the noise. And the other thing that we saw is that this kind of allows us to think about these kind of multivariate p-dimensional problems as just p one-dimensional problems, and that's very useful. So extensions beyond this are possible, and they're pretty natural. It's just a little bit more notationally heavy and a bit more challenging. Okay, so now so since x transpose x over n equals the identity, that's our assumption. We know that B hat L is unique because obviously, that kind of means that, we can actually, like, the rank of x is P, that naturally follows. And, it also means that, okay, and so just to remind everyone, so we're going to kind of use this idea of subgradients. So we have that f of b here equals okay, and so the gradient here okay, and so remember that this z here, zj, so z is just equal to that's going to be equal to +1 if bj is bigger than 0, -1 if bj is less than 0, and it's in, like, it, coming from this subgradient, it's if bj is equal to 0, it's equal to any number between -1 and 1. So the condition for B hat L is that this gradient, I'm using this notion gradient even though so this is actually subgradient, but I'm using the notation the same, so it's a slight abuse of notation here. So the subgradient equals 0. So therefore we have that so we can re-express this as, sorry. Okay, and I'm writing z hat L here because it's a function of the lasso estimator, and we know that so since we have that x transpose x over n equals the identity and y tilde equals x transpose y over square root of n, then what we have here is and And we can express this one coordinate at a time. So beta hat Lj is just z hat Lj over n. Okay, and so what that means is that, so if beta hat Lj is bigger than 0, then we know that z hat Lj is equal to 1. If beta hat Lj is less than 0, then we know that z hat Lj is equal to -1. And if b hat Lj equals 0, then z hat Lj is in -1 to +1 using that definition. So what that essentially means is that and we did work this out in the previous lecture, but I'll just do it again. It's and then it's going to be 0 if it's going to be 0 otherwise. So therefore so we're going to have b hat Lj is equal to 0 if y tilde j over square root of n is between lambda over n and negative lambda over n. Okay. And so as I mentioned, this is referred to as soft thresholding up. And the reason it's called soft thresholding is it thresholds things to 0 if your y tilde j is too small, essentially. But if it's bigger than that required threshold, then it's not exactly y tilde j. It subtracts off this, and so in terms of a graph, we can kind of see that if you want to look at b hat Lj versus y tilde j over square root of n, it essentially just looks like this. So we can see that this is the region where b hat Lj is equal to 0. So we kind of clearly see that if the y tilde j over square root of n is less than or equal to lambda n. Okay, and so and then I just want to point out that for least squares, if x transpose x over n equals the identity and y tilde equals x transpose y over square root of n, as we have here, then we have that beta hat, I'll use this notation, beta hat ls is just equal to y tilde over square root of n, i.e. like beta hat ls j equals to y tilde j over square root of n. And then for ridge regression, if like we saw in a couple of lectures ago, then we have that beta hat ls is equal to y tilde over square root of n, and then we multiply this by this kind of this other shrinkage term, which is 1 over 1 plus lambda over n. Okay. So this is beta at R. And so for the lasso, we know, so note lambda over n controls shrinkage or regularization. And for the lasso, we can kind of write this out as beta hat L is equal to, I'm using this notation as the soft thresholding operator, which I'll y tilde over square root of n, where we can say that soft thresholding operator which is st of some x is equal to x minus t if x is bigger than t, x plus t if x is less than negative t, and then it's equal to 0 for absolute value of x less than or equal to t. So that's the soft thresholding operator, and so you can write b hat L as in that way. So essentially you can see that lambda over n controls regularization or shrinkage. But the lasso and ridge estimators basically do them in different ways, and the least squares does it kind of in does no regularization at all. Okay. So I'm just going to briefly mention, just for a couple of minutes, other algorithms in case you're, if you read about that lasso and sort of read other algorithms that people look at. One is coordinate descent. And again, I'm just kind of mentioning these names. So if you want to read more about them, you can, but they're not really covered in the homework or anything. So coordinate descent, which essentially, it's like gradient descent, but you only take gradients for specific coordinates. And why we do this for the lasso is because it encourages sparsity again, because it only moves along one coordinate at each iteration. So this is also related to this is actually identical to soft thresholding. If you only do one round. And so, you can use other algorithms. Coordinate descent's probably is one of the more widely used ones because it's very related to soft thresholding. But there's other kind of subgradient based methods that people also use. And I also just wanted to mention that there's this R package, GLMnet. Which allows you to do L1 regularization for any GLM family. So we've kind of shown it only in the case where we have the normal distribution or least squares as the objective. But for example, if you were looking at logistic regression or Poisson regression, you could also add an L1 penalty, and the GLMnet package allows you to do that. And that's one thing you'll be using in homework 3. So okay, and if some of you may not have used these packages before, and that's okay. Usually, like if you haven't used a package, if you are not sure what to put in as kind of inputs, the help function is very useful. But yeah, feel free to contact me if you're having trouble kind of using these packages. So now we move on to the fourth component, which is the analysis. And this is kind of going to really illustrate why we want to, why we potentially want to do shrinkage or regularization, and also going to give us some insight as to how to choose lambda, which I haven't really touched on yet. So one thing to note here is that, or we're going to assume again that because it's, again, that x transpose x over n equals the identity. And then we're also going to use this notation that y tilde equals x transpose y over square root of n. And so we know that just equals the square root of n b plus epsilon tilde, where epsilon tilde is multivariate normal with mean 0 and covariance sigma squared I p by p. Okay. So remember that B hat L is equal to this soft thresholding operator y tilde over square root of n. And so just to write it out fully, this is equal to y tilde over square root of n. Or let me just say that B hat L j is y minus lambda over n. And, so we have this kind of shrinkage to 0 if the absolute value of y tilde j over square root of n is less than or equal to lambda over n. Okay, and so what we have is okay, so now I'm just substituting in, since we know that y tilde j over square root of n is just bj plus epsilon tilde j, I'm just substituting that in. So I'm just substituting that in here, and we get this this expression. So one thing to note is that so if you look at it coordinate by coordinate or variable by variable, if b hat lj and bj are both 0, which is possible with this shrinkage estimator, then we have b hat lj, then we have 0 error, and so otherwise. So otherwise we have an error otherwise you can see that we have this error that's is equal to sigma squared over n, and so plus lambda squared over n squared. Sorry, let me just be clear. So beta hat Lj is not 0 and Bj is not 0, or I should just say if beta hat Lj is not 0, then we have this this expression. And the other case to worry about is equals 0, but Bj is not 0, then that is just going to be equal to Bj squared. Okay, so we kind of have these three different cases to think about, right? So this relates to this very important question of, this relates to how do we choose lambda? How do we choose lambda? So we want to ensure that if Bj is 0, then B hat Lj is also 0. And we also want to ensure that if Bj is not 0, then B hat Lj is also not going to be 0. And so if we plug in Bj equals 0, let's see what happens. Then we have so if Bj equals 0, B hat Lj will equal 0 only if you can see that, looking at this expression up here, the Bj will disappear, and it's only going to be true if and we want this true for all j. So therefore we want that such that so we're going to say that we want the maximum value of j less than 1 to p, or equivalently that okay, so this is this is potentially a little bit non-intuitive, and you may not have seen an argument like this before. But this essentially, like what we're doing is, we want any y tilde below the noise level is thresholded to 0. So any we want to choose lambda large enough, because if you choose lambda equals 0, you just get the least squares estimator, but that's not going to shrink things if bj is 0. And so we want to choose lambda such that the square root of n times the maximum j of these normal random variables is 0. And so I'm going to present a useful fact that you don't need to know sort of where I got it from, or we're not really going to use this result anywhere. So you don't it's just a useful thing to it's a true property that's very useful to see the mean squared error for the lasso, and then how it compares to the mean squared error for ordinary least squares. So if we're taking the maximum of a bunch of p Gaussian variables, so the expectation of that thing is equal to so this is a random variable. I believe it's equal to 2 times square root of log p. So the proof for this, if you're interested, I can point you to references, textbooks on concentration of Gaussian variables, which is a bit beyond what we're going to cover in this course. Okay, and so therefore we're going to just choose lambda to be bigger than 2 times square root of n times log p. So, and sorry, this should have a sigma squared in it. So 2 times sigma times square root of n times square root of n log p. So remember that epsilon tilde j is normal, mean 0 and variance sigma squared, and so this is how we're going to choose this lambda. And then using some simplifications, we get that, this thing is going to be equal to 0 if bj is 0, and if it's not 0, then we're going to get bj is not 0. Okay, and so therefore if we look at the overall mean squared error, you're only going to sum over the j such that bj is not equal to 0, and you're going to get that this is sigma squared over n plus lambda squared over n squared. And then you also know that lambda is equal to 2 sigma times square root of n log p. So therefore, you're going to add up sigma squared over n plus 4 sigma squared log p over n. Okay, and so you're subbing in, since we know that the norm of b0, which is the sum of j, sum of j equals 1p, indicator bj not equal to 0, we know that that's less than s. Then we know that this mean squared error bound, which is pretty sharp, is going to be s sigma squared over n plus 4 s sigma squared log p over n. And so just to give some intuition behind this, this is the error in estimating the S non-zero coefficients. And this is the error because we don't know which of the p coefficients is non-zero. Okay, so yeah, in the last minute or two, I'll wrap this up in the next lecture, but in the last minute or two, I just wanted to note that recall that this is p sigma squared over n, whereas so we know that this is less than s sigma squared over n plus 4s sigma squared log p over n. And so if 4s log p plus s is smaller than p, then beta hat L gives a smaller mean squared error than beta hat LS. So if S is small, B hat L is usually much better than B hat LS. Okay, and we're going to wrap this up and just wrap up this whole topic on regularization in general in the next lecture. All right, thanks. That's